Section: Introduction. In this section, we introduce foundation models, particularly large language models, LLMs, that use transformer architectures. These models show that extensive training on general tasks, like predicting the next word, can lead to strong generalization across various tasks and areas. During training, we also notice the emergence of important skills like reasoning and prompting. However, we encounter a surprising phenomenon called grokking, where generalization improves significantly even after the training loss has stabilized, which usually indicates overfitting in traditional machine learning. We observe that while there is a shift from memorization to generalization during grokking, it raises questions about how and why this transition occurs when the training loss has plateaued. Previous studies on grokking have focused on smaller models trained for many epochs on specific tasks, but LLMs are typically pre-trained on large datasets in just one epoch, which may include diverse and noisy data. This leads us to wonder if grokking occurs during the pre-training of large models, especially since each sample is only seen once. We find it unclear when different samples are memorized and whether they are memorized simultaneously. Additionally, without revisiting the same data, understanding how memorization turns into generalization is challenging. We ask where the generalization ability of LLMs originates, when it happens, and if it depends on prior memorization. Unfortunately, we cannot rely on training loss dynamics to answer these questions, as generalization performance can still vary even when training loss has plateaued. Monitoring generalization during LLM pre-training is also costly, as we need to fine-tune a pre-trained model before evaluating it on downstream tasks. To address these issues, we aim to develop an efficient metric that accurately reflects generalization dynamics during pre-training. Our main contributions include investigating the training dynamics and potential grokking in LLM pre-training to understand how generalization emerges in downstream tasks. We focus on the open-source checkpoints and data for pre-training a practical-scale LLM called OLMOE, which has 7 billion parameters. For the first time, we confirm that grokking occurs during LLM pre-training, but it is local and asynchronous across different data groups. This means that the model memorizes various domains at different training steps, taking different amounts of time to generalize to related test tasks. As a result, generalization performance is often unstable in the early stages of pre-training but improves steadily once enough data is memorized. We also find that the difficulty of the data affects this process, with later memorized data taking longer to generalize. Since training loss converges before grokking begins, explaining how continued pre-training leads to improved generalization is complex. To clarify the memorization-to-generalization mechanism, we analyze the hidden states of LLMs, focusing on the pathways in OLMOE, which represent the expert choices for each sample. We introduce two metrics to measure pathway complexity and its changes over time: the edit distance between pathways of different samples and the consistency of expert embeddings across layers for individual samples. Our analysis across 4 domains reveals a significant trend during grokking. As more data is introduced, the edit distance decreases and consistency increases. This indicates a reduction in pathway complexity and a more efficient memorization process that utilizes shared knowledge across samples, leading to better generalization. We also provide a theoretical explanation connecting pathway complexity to a generalization bound for a one-layer mixture of experts model. Practically, our two metrics correlate strongly with test performance after instruction fine-tuning, offering a useful tool for monitoring generalization during pre-training without needing a test set or fine-tuning. This work represents a crucial step in understanding grokking and the memorization-to-generalization mechanism in LLM pre-training by systematically analyzing pathway complexity dynamics in a mixture of experts LLM. Our key findings include that grokking occurs during one-pass pre-training of practical-scale LLMs, but it is local and asynchronous for different data groups. We also explain the memorization-to-generalization mechanism through the dynamics of LLM internal states, showing that smarter memorization leads to better generalization. Section Summary. In this section, we explore the phenomenon of grokking in large language model, LLM, pre-training, revealing that while generalization improves after training loss has plateaued, it occurs locally and asynchronously across different data groups. We introduce two metrics to analyze the dynamics of LLM pathways, demonstrating that as memorization becomes more efficient through shared knowledge, generalization performance increases, providing a practical tool for monitoring this process during pre-training. Section: Related work. In this section, we review related work on Grokking, which has mainly concentrated on smaller models and simpler tasks. The phenomenon was first noted by researchers who used a two-layer transformer on a small algorithmic dataset. Later studies expanded this to shallow transformers, densely connected networks, and CNNs. Importantly, these studies utilized multi-epoch training, which is quite different from the one-pass training typical in large language model, LLM, pre-training. While some examined Grokking in a 162 million parameter transformer trained on 40 billion tokens for a copying task, the scale and simplicity of their approach do not reflect real-world applications. In contrast, we are the first to explore Grokking in a 7 billion parameter LLM across a variety of practical tasks, such as mathematical reasoning, code generation, common sense understanding, and domain-specific knowledge retrieval. Several studies have aimed to uncover the mechanisms behind Grokking. Some demonstrated that Grokking arises from structured representations that develop during training, while others linked it to the gradual enhancement of structured mechanisms in model weights. One study associated Grokking with subnetwork sparsity in a single-layer ReLU network, and another found that decision boundaries smooth out during the Grokking phase in CNN classification tasks. Additionally, some identified early training loss patterns as indicators of future Grokking. Our research, however, offers a new perspective on Grokking in larger LLMs through an interpretive analysis of mixture of experts, MO, architectures, and introduces practical indicators for monitoring generative behavior during LLM pre-training. We also address the challenge of understanding when and why models start to generalize during large-scale pre-training. It is commonly believed that generalization occurs once training loss levels off. However, studies on small synthetic tasks show that models often first memorize the training data before suddenly achieving high test accuracy, indicating a significant delay between memorization and generalization. We provide the first empirical evidence that this delayed generalization also happens in LLM pre-training, demonstrating that training loss is not a reliable indicator of generalization, as it can diverge in both timing and scale. We support this with two perspectives, one showing that overall training progress does not always lead to improved test accuracy, and another revealing that generalization often lags behind training, especially for more challenging examples. These findings challenge existing assumptions and underscore the need for better metrics to track generalization in LLMs. To analyze how generalization develops during pre-training, we first isolate a subset of training samples that the model has learned reliably over time, which we call Grokking data. This term highlights the shift from mere memorization to the formation of structured, generalizable representations. By identifying this data, we can focus on the accumulation of stable internal knowledge that supports downstream generalization. We track each sample's loss trajectory using cross-entropy loss and define a sample's Grokking time as when its loss meets specific stability criteria. This filtering ensures that we are observing robust learning rather than fleeting memorization. We use Grokking data to monitor training progress and its relationship to generalization across 4 domains: arithmetic reasoning, code generation, common sense question answering, and domain-specific question answering. Our analysis shows that training and test dynamics vary across these domains. In some cases, training samples converge while test accuracy remains stagnant. In others, accuracy improves early but then declines before significant convergence occurs. These patterns indicate that memorization and generalization do not progress uniformly across tasks. Even as the model learns and memorizes training examples, improvements in test accuracy can be delayed or disconnected from convergence trends. This insight suggests that relying solely on convergence metrics can misrepresent when and how generalization occurs, highlighting the need for more informative indicators. Section Summary. In this section, we review previous research on Grokking, which has largely focused on smaller models and simpler tasks, and we highlight our novel investigation of Grokking in a 7 billion parameter LLM across diverse, practical tasks. We present empirical evidence of delayed generalization during LLM pretraining, demonstrating that training loss is an unreliable indicator of generalization, and we analyze how generalization unfolds asynchronously across different domains, revealing that training progress does not consistently correlate with test accuracy gains. Section: Group-level analysis, later grokking and longer delay for more difficult data. In this section, we analyze group-level dynamics to understand the relationship between memorization and generalization in our model. We begin by tracking when individual training samples are learned, using specific grokking times to identify samples that are learned stably. We categorize these samples based on when they start to generalize. For the test set, we also classify samples that eventually generalize, ensuring they haven't been exposed during training by using membership inference attacks. We monitor their prediction progress and group them according to when their predictions become consistently accurate. To connect training improvements to testing outcomes, we match each training group with a similar test group by computing embeddings and using an optimal matching algorithm. Our findings show that training loss stabilizes before test accuracy improves. For groups that converge early, the gap between convergence and test improvement is short, while later converging groups experience a longer delay, often needing more training steps before generalization occurs. This delay indicates that the model needs time to not only memorize data but also to reorganize its internal representations for better transfer to new examples. We observe that this delay is not random. It correlates with the difficulty of the samples, suggesting that the complexity of a pattern affects both learning and generalization times. Thus, at the group level, training loss alone is not a reliable indicator of when a model is ready to generalize. We raise an important question: what internal changes happen in the model that lead to this sudden ability to generalize? Understanding this is crucial for improving diagnostic tools, training efficiency, and uncovering how large neural networks learn. Next, we focus on the dynamics of routing pathways during grokking. We note that grokking represents a shift from memorization to generalization, which traditional metrics like training loss do not fully capture. In our mixture of experts, MO, architecture, each input activates only a small number of experts, creating a routing pathway that reveals the model's internal decision-making. We introduce two metrics to analyze these pathways: the similarity of pathways across different inputs and the consistency of a single input's pathway. By focusing on grokking samples, we can study the transition from memorization to generalization beyond just loss convergence. Our analysis shows that as training progresses, pathways evolve from random and specific to more structured and shared among similar inputs, indicating a transition from memorization to generalization. We hypothesize that as the model generalizes, it shifts from individualized computations to shared, structured computations, which we measure by examining how expert pathway similarity changes during pre-training. We define each input's pathway as the sequence of selected experts through the layers of the MO. We quantify pathway similarity using sequence edit distance, which measures how many changes are needed to transform one sequence into another. Our results reveal a clear pattern. Early in pre-training, inputs follow similar routes, resulting in low edit distances. As training continues, pathways diverge, but this divergence reverses once convergence occurs, with inputs of similar content being routed through similar expert sequences. This indicates that the model is finding common computations for related inputs, marking a clear sign of generalization. Interestingly, this transition varies across different layers. Shallow layers show the most significant decreases in edit distance at the grokking point, while deeper layers exhibit smaller changes. Notably, the final layer shows an increase in edit distance after grokking, suggesting that while early layers converge towards common pathways, later layers maintain flexibility, balancing shared representations with task-specific needs. Section Summary. In this section, we analyze the relationship between training and generalization by tracking when individual samples are learned and how their prediction trajectories evolve, revealing that generalization often lags behind training loss convergence, particularly for more complex data. Our findings indicate that as models transition from memorization to generalization, their internal routing pathways become more structured and shared across similar inputs, highlighting a significant decoupling between memorization and effective transfer to unseen examples. Section: Pathway Consistency and Complexity for Single Samples. In this section, we explore how the complexity of routing for individual inputs changes during pre-training. We believe that a more consistent selection of experts across layers indicates that the model has found a generalizable way to process information. To measure this, we introduce a metric for single-sample pathway consistency, which looks at how smoothly experts transition between layers. In a typical mixture of experts (MO) setup, the router at each layer is a simple model that calculates scores for selecting from multiple experts. We represent the router's parameters with a weight matrix, where each expert's embedding captures its characteristics. These embeddings help determine which expert to use based on the input features. Although these embeddings remain constant, their arrangement influences expert selection during inference. To assess how smooth the routing is, we define pathway consistency as the average similarity between the embeddings of consecutive layers for a given input. A higher consistency value indicates erratic transitions, while a lower value suggests smoother routing. We observe that even after the training loss stabilizes, pathway consistency continues to improve, indicating ongoing refinement in the model's routing strategy. This suggests that smoother transitions between layers develop even after the model's performance appears stable, making pathway consistency a useful tool for understanding the model's internal organization beyond just prediction accuracy. Next, we investigate how our pathway metrics relate to test performance across different tasks. We calculate correlations between test accuracy and two metrics: the similarity of pathways and the consistency of pathways across layers. We define the global Grokking point as the moment when test accuracy starts to rise consistently, allowing us to focus on the mechanisms that drive generalization after this point. Our analysis shows that pathway consistency has a strong positive correlation with test accuracy, often exceeding 0.97, indicating that stable routing is crucial for generalization. In contrast, the similarity of pathways shows strong negative correlations, suggesting that as generalization improves, inputs tend to follow more similar routes. We find that traditional loss metrics do not align well with generalization, as they sometimes show unexpected positive correlations with test accuracy. These results highlight pathway metrics as reliable indicators of generalization that depend solely on training dynamics, making them particularly useful for real-time monitoring in various settings. Finally, we establish a connection between expert routing patterns and model generalization through an analysis of the routing mechanism's complexity. We identify that the effective complexity of routing is a key factor in MO generalization. Our theoretical framework explains the Grokking phenomenon, where the transition from random to structured expert activations leads to significant improvements in generalization. For more details on our theoretical setup and proofs, we refer to the appendix.